The long-anticipated launch of the James Webb Space Telescope is now slated for Christmas Day, a new window to the stars. Welcome to Techstination. I'm Fred Fishkin, along with Bob Vanderbei, a professor at Princeton University and the Department of Astrophysical Sciences and co-author of Sizing Up the Universe. Hi, Bob.
Hello. This is good to be here with you.
Thanks, Bob. And we are very happy to be speaking with Dr. Jane Rigby, Operations Project Scientist for the James Webb Space Telescope. Thank you for taking the time with us.
Hi there. It's good to be here.
Well, you've been an astrophysicist at NASA's Goddard Space Flight Center for more than 11 years. So hopefully this Christmas launch will be quite a gift. Something like 25 years in the making?
Absolutely. Yes. Webb was conceived in the 90s. I started working on it 11 years ago, and I'm so excited to finally be getting this telescope up into space to do its science.
What are some of the things that we hope the Webb telescope will reveal?
So the Webb telescope is going to be so much more powerful than Hubble. It's designed to do the things that Hubble can't. It can see objects in the same amount of time that are 100 times fainter than what Hubble can see. And so we're going to be doing hundreds of different science programs in the first year alone. But some of the big science programs that we're going to be doing fall into these couple categories. We're going to be studying how galaxies evolved over cosmic time since the first galaxies formed. And one of the big science goals for Webb is to find that first generation of galaxies that formed after the Big Bang. And that works because telescopes act like time machines. We're seeing so far out into space that the light we're seeing arriving now has been traveling through space from almost the whole history of the universe. So we're seeing galaxies where that light left only 200, 300 million years after the Big Bang. So we're going to be looking back across cosmic time and seeing how it all got started. How did galaxies like the Milky Way get started? And then how did they evolve over 13 billion years to be the places that we call home?
Simply amazing. And this will work in conjunction with Hubble, at least on some of these things?
Yeah, so the Hubble Space Telescope, Hubble and Webb are very complementary. We knew that Hubble was up and working, and we're counting on it to keep working for several more years. And so Webb was designed to do the things that Hubble can't. So Hubble works mostly in the ultraviolet and the optical, so bluer than we can see and the light that we can see. But it's a warm telescope, it's room temperature, so it's not very good in the infrared. Those first galaxies that we want to study, that light has been shifted by the expansion of the universe from the optical and the ultraviolet to the infrared. So we need an infrared telescope to study these galaxies. And so to do that, it's got to be cold. And so the Webb telescope is designed to work in the infrared and to be very, very cold, only 40 or 50 degrees above absolute zero, so that it can see that faint heat from the dawn of everything, from the light of the first galaxies.
Bob?
That's awesome. I can hardly wait. 200 million years after the Big Bang. I mean, the Milky Way rotates once every about 200 million years, that's my understanding. So you're basically seeing these galaxies maybe rotating at the same speed. And so that's like in the first rotation of their existence or something like that, maybe.
If they're rotating, if they're smooth, if they've made structure, probably one good guess would be that first generation was very messy, right? And that you've got tons of infall and accretion and galaxies that are grabbing other galaxies and merging, and that it's this messy, ugly process. And so it may look very different from the sort of staid, mature galaxies like the one we live in today.
Yeah, how many billions of years does it take for the blob to flatten out into a disk?
We don't actually know how disks form. We see that disks are rarer in the early universe, looking back to about, those studies have been done well to about 7 billion years in the past. And we can see that definitely making smooth disks like our Milky Way happened fairly recently, the last half of the history of the universe.
Yeah, interesting.
One of the things that you're going to be using this for is to help advance the search for life beyond our planet. Tell us how that will happen.
So Webb is going to be doing hundreds of different science programs in the first year. About a quarter of all the programs are to study planets orbiting other stars, exoplanets. And so there's a lot of different exoplanets we want to study. Some are Neptune-like or Jupiter-like, or planets where there aren't any good analogs in our solar system. So that's really cool. We want to understand how planetary systems are formed, and how they evolve. There's also, of course, a ton of interest in planets that are like ours, planets that are rocky, that could have liquid water on them, oceans, and that are the temperatures, sort of moderate temperatures. That, in our experience from our sample of one, is the kind of environment where life got started. Webb will not be able to say, yes, that's the right planet. That planet has life. You got to build a whole new next generation telescope for that. And that's in fact something that there's just been a big report out from an every 10-year survey of astronomy, where that was the top recommendation of that blue panel report, was we should build something that can go survey nearby planets and tell us which ones have life. What Webb can do for the nearest stars, that which tend to be little red dwarfy things, with planets that are orbiting very fast, like once a month, so those sorts of systems, might be habitable. And Webb can tell us whether there's whether there's water vapor present, whether it looks like that's the chemistry that looks not too hot, not too cold, kind of Goldilocksy, right? But that's a very different thing from saying, yes, there's life there. So Webb can tell us how common are habitable planets, right? And then it would take another telescope after that to tell us, okay, fine, which ones have life?
Now, getting this launched, hopefully on Christmas Day, things can change with weather, as we've seen, but that's just the beginning of the number of steps before this is put to work. Describe for us what's going to be going on over the next few months to get this operational.
Absolutely. So launch is the easy part, right? We put it on a rocket with a whole lot of hydrogen and send it up. Launch is actually easy though, because the telescope is folded up inside the rocket. It's a much bigger telescope than can fit in a rocket. And so the sun shield is all folded up. The telescope is folded up. And then once we get into space, we have to unfold the telescope. And so this is one of these some assembly required, right? This is 2 hard weeks, more if we run into difficulties of unfolding this telescope in space. And so that's, I would say, the most challenging part of the mission. That's something that has never been done before on this scale. This is a hard thing. So we're unfolding the telescope and we're unfolding the sun shield that protects the telescope and lets it get very cold. That process will take up to a month, a couple weeks, and then we start cooling down. So the telescope, right? This is what Webb looks like once it's deployed, right? There's this 5-layer sun shield. It's actually made of like it looks like potato chip wrappers. It's this thin metallized plastic, and then the telescope is here. So as soon as the sun shield comes out, the telescope's hiding in the shadow of the sun shield. The sun's down here. And so this starts chilling very quickly. And so over the course of 100 days, the telescope goes from being room temperature to being 40 to 50 degrees above absolute zero. So incredibly cold. That process takes 100 days. While that's happening, we're taking these mirrors, which when they launch are off with respect to each other by up to, ½ an inch. And we are driving them to work together like one mirror instead of 18 little segments. And so that process has to align those mirrors to better than, it's better than a human hair. It's a couple viruses across, right? It has to get these really closely aligned. That process is a several month process. And then we have to check out the 4 science instruments that are on the back here and get those working as well so that we're ready to do science. So it's going to be a 6-month wait. I know we're also excited, but it's going to be a 6-month wait between it launched. We'll know within a month that the deployments are working, but then it's 6 months from launch to get the first amazing data.
And it flies out there at the Lagrange L2 point, which is 4 times further away than the moon. How many days of that first month does it just take to get there?
So yes, so Webb orbits the second Lagrange point, which is, as you said, 4 times past the distance of the moon. It's a nice stable point. It's a nice thermally stable place. There's always the same amount of sunlight. There's always the same amount of reflected Earth light. We have to spend some energy to stay in orbit about that. It takes about a month to get there, but we're not waiting. It's not like we're going to be doing things the whole time. So, as we're on the way out, we're going to be unfolding the telescope, right? We're going to be deploying this secondary mirror that has to come down. We have these mirrors. You can see 3 mirrors on either side are folded up for launch. So we have to unfold those, right? So we're doing all that work, and the sun shield, which as well has to get unfolded and deployed as well. So all of that is happening on the way out to L2.
Interesting.
I assume this means that unlike Hubble, that needed some fixing, I guess, before we had some really wow moments. There's no real possibility of doing fixes as we go along, or is there?
Webb is not serviceable. This is not a telescope that we can send humans up to go fix. It is going to a place that is 4 times further than humans have ever been. So it has to work the first time, and it has to work in deep space. And there's no rescue if there's no rescue by humans. So we spent a tremendous amount of time testing it on the ground, doing all of these deployments of the sun shield on the ground, testing the mirrors in the world's largest vacuum chamber, chilling them down, putting them in a vacuum, testing that the mirrors are indeed the right shape and not the way Hubble was, the wrong shape. So we've done all that to test that it works on Earth, so it's going to work in space. But that said, these deployments, this is the most complicated thing we've put in space to do science. And there are several hundred deployments that all need to go well. And there's things that we can do if we run into issues. We practice that over and over. But I don't want to sugarcoat this. This is a difficult thing we're doing. But there's just no way around it. If we're ever going to build telescopes bigger than the rockets, if we're going to build big telescopes and put them in space, we have to either unfold them out of their rockets, or we need to launch them in pieces and put them together in space. It's just, rockets can only be so big.
What's the estimate as to when we might have your first images that we'll be able to see and share?
So we'll know that the telescope is working. We'll know that the major deployments work within a month, and we'll be providing updates as we go. We'll know that the telescope is working within about 120 days after launch, right? Yes, we're happy with. We're making crisp, sharp images. But to get those first images, then we have to get the science instruments commissioned. They will be waking up, and we'll be getting those working and checking those out. So it's 6 months to get the first gorgeous data. And I know that's a long wait. I want to see it too.
I'm sure everybody there is anxious. Go ahead, Bob.
When you're doing that first image, everybody will want to see that first image. And I'm just wondering, is it going to be a galaxy or just a nearby star that you're trying to calibrate things on?
So first, when we're doing the mirror alignment, right, when we're getting the mirrors to behave, that will be looking at some bright stars.
Yeah.
They're fainter than your eye can see, but they're still pretty bright. Like you could see them with a small telescope on Earth. And at first, the first images that Webb takes, all of these 18 mirrors are kind of pointed every which way. And so it's ugly, but we know that, right? We have rehearsed in great gory detail every stage of taking what will be at the beginning 18 blurry images, because each of these little mirrors is acting like its own telescope, right? It's like getting all of them to sing in the choir versus just singing whatever it is that's in their heart at whatever tempo and pace, right? And we know that. That is the work that we have to do. So very methodically, with this process that is worked out with every detail and every contingency in these god-awful biggest spreadsheets I've ever seen, we work out how you drive those 18 mirrors all singing their own song to working together as one telescope that is sending the light collectively to the secondary mirror and then into the science instruments. So it's working as one telescope instead of 18.
And then everybody's going to be excited, I suppose, about the first galaxy. Has it been announced which galaxy will be the first one?
So NASA's keeping that a secret, what the first gorgeous images will be. All we're saying is that they'll knock your socks off. They have to demonstrate that all 4 science instruments work. And if we're looking at distant galaxies, we don't just get one galaxy, right? It's like the deep fields. Everywhere Webb looks, it's a deep field.
Yeah.
So it's a bigger field of view than Hubble and much deeper, 100 times deeper. So if you think about the deep fields that Hubble has taken, right? The deepest field would be the ultra deep field, which is, I think, it's about a little bit more than 2 weeks for Hubble, right? Webb can take that, go that deep in less than a day.
Wow.
And Webb is planning to spend several weeks on some of these fields. So if you think about the beautiful ultra deep fields with all the galaxies sprinkled all over, now look at the black parts of that image where you don't see anything.
Right.
And imagine, all of those faint galaxies coming into view. That's what I'm hoping we'll see.
I can hardly wait.
We all can hardly wait. Jane Rigby, we know you have to go, and we really appreciate you spending time with us, and thumbs up here.
Happy to help.
Well, the telescope is named after James Webb, who headed NASA in its infancy under Presidents Kennedy and Johnson when the U.S. first launched astronauts into space. Again, the launch is scheduled for Saturday morning from Europe's spaceport in French Guiana. Bob, as someone who spent so many nights peering into space, taking amazing images, I might add, even from a telescope in your driveway, what does this mean to you? I guess we're lucky to be alive to see this, for one thing.
Well, I think it's awesome to be able to take images of galaxies, because that's the most difficult thing in my driveway, because light pollution from New Jersey isn't the greatest. But even if I've been out to dark places, and even there, the number of galaxies one sees or takes a picture of with a moderate size, equipment is not a huge amount. And so the Hubble Ultra Deep Field was awesome when that got released, because it's like, wow, look at all those galaxies. And another thing I like to think about is astrophysicists have done these kind of analyses and calculations, and the number of galaxies in the universe is about equal to the number of stars in our galaxy. And so if you look at a picture, you should be able to see the same number of galaxies as you see stars. And you see these pictures with lots of stars, and there's a couple galaxies I see here. So I'm really looking forward to the James Webb, because maybe we'll see just a bazillion galaxies together with a bazillion stars.
Are there any specific types of images or things that you're hoping to see or learn?
Probably nothing specific. Well, of course, as she talked about, finding life on other planets and habitable planets, detecting habitable planets would also be something I'm particularly interested in. And I don't know the details of how the James Webb Space Telescope is going to make those detections. And had she been here longer, I would have asked her about that, because as she did sort of indicate, JWST is not going to take pictures of planets, because the planets are too close to the star to be able to do that with JWST. And that's one of the things I worked on for some years, was a different telescope that got canceled, unfortunately, called TPF, which was going to be able to take pictures of planets near stars. But there's all kinds of things you can do to, as she was saying, detect oxygen or detect water by looking at a spectral analysis of the light that you're getting. So you're just looking at what you think is a star, but you're getting a spectral analysis, and you're seeing stuff that wouldn't be from the star. It would be from a planet near that star. So I'd love to learn more detail about how, and I'm sure I will learn more detail in the future about how JWST will do that. And so that's one of the things that will be very interesting to me. Yeah.
I didn't get to ask Jane about it, but maybe you have some thoughts. It's as somebody who covers consumer technology, the idea that they started building something like this 25 years ago, the way technology advances, how do they keep up with the sensors and the technology, the computing power that would go into something like this, and constantly get it ready? Okay, now we're set.
Yeah, that's another question I actually wanted to ask her. Because when I was working on this other space telescope, the whole idea of making a similar tool to attach to the James Webb Space Telescope was something we wanted to propose. But this was like in the year 2006, I think, or 7, when we started talking to the JWST people, and they said, that's awesome what you're proposing, but the whole design is locked in. We can't change anything. And that was in 2007. So I'm guessing with the various delays that have happened, some things did get changed, and the computer technology and imaging technology has improved dramatically in the last 15 years. So I'm guessing that's been improved over the years, but I actually don't know. That was one of the things I would have liked to have found out from her, but I'll have to ask her later.
Well, we want to point out that you've got a new book coming out next spring as well that you've co-authored. It's called Welcome to the Universe in 3D, a visual tour. Tell us a little bit about that.
So here's the book.
Okay.
Welcome to the Universe in 3D. It's a book. And if you open up the front, it just looks like a book. Although everything is organized not to be read this way, but to be read this way, which is a little bit unusual for books, but it's okay. And every page has a stereo picture at the top and text describing what you're seeing at the bottom. And the way you look at these is because in the back of the book, there's a little piece that flips out here. And then you hold this up and hold this up. Maybe I'll demo it for you. You take off your reading glasses, maybe, at least I do, and you hold it like this. So here, so the pictures are here. There they are. The glasses are here, and you hold this up, and you put this up to your face. I don't know if you can see me because all I see is the book right now. And you look at it. Oh my God, it's 3D. Wow, that's beautiful. And so that's what the surface of Venus looks like in 3D.
You know, and that's the publication date is in April, and we encourage everybody to keep an eye out for that. You can already find it on Amazon, the preview kind of thing. But finally, you know, and I want to pose the question that a lot of people raise from time to time, you know, having listened to Jane and listened to you. What are your thoughts about why this is important that we do something like the Webb telescope? People wonder, well, we have so many problems here. Why are we bothering spending money on something like that?
Well, I think science is important in general. We would imagine what life was like 5,000 years ago on Earth for Homo sapiens, you know, they had some food that they had, you know, it was just a much different life. And a lot of many things have improved, politics and management and stuff, but look over the last 300 or 400 years, and a huge amount of the improvement in life has been because of scientific understanding, discovery, from, you know, making cameras and making computers and artificial intelligence and machine learning so that your computers can seem like they're almost as smart as humans these days. I mean, this evolutionary stuff of science is dramatic. And I think understanding the astro world is also extremely important, not just understanding what's in our solar system and where can we go in here, but what's the whole story. And you know, this might not affect our lives in the near future, other than just our curiosity, but in the long term, it might make a huge difference. We might actually figure out someday, I don't know if this is true, but we might figure out someday how to travel places faster than the speed of light by going through wormholes or who knows what. You know, people don't know today how this might be possible. But maybe if Homo sapiens, human beings, continue to understand science better and better, not over 100 years, but suppose we do this over 1,000 years, or maybe hundreds of thousands of years. Imagine how smart we can be hundreds of thousands of years in the future, and maybe we can figure out how to go to other planets. And we might need to if Earth doesn't become a very manageable environment for human beings anymore. The sun eventually, well, this is billions of years in the future, but the sun will eventually get old and die. And there's a whole process there. And before it completely dies, it's going to kind of get larger. And the surface of the sun is going to come out further than Earth. Now, this is, I think, like 4 billion years in the future, so you and I won't be here, but things do change, and understanding how that change happens and what the implications are is important long term. And so I don't think we should just not do it because it won't help us 5 years from now or 50 years from now. I think we should, I don't think we should spend 100% of our money doing this, but we should always spend a reasonable fraction of money doing research, even if that research is about helping in the distant future.
So, Bob, let's give our audience a taste of some of the things that you've been able to accomplish with the 3D imaging that you talked about.
Yeah, so NASA is releasing new image data of Jupiter from the Hubble Space Telescope. They don't release it as a 3D picture like what you're seeing here. They release it as just a picture, latitude and longitude, if you like, and just what's there at that latitude and that longitude. So it's a little rectangular picture you can download from the NASA website. And they put a new version of Jupiter out there just the other day. They have pictures of the Jupiter's moons and the other planets in our solar system. And so because this new one came out, I downloaded it the other day and made this 3D version. And I thought it would be fun to add to it the 4 Galilean moons of Jupiter, which you can see orbiting Jupiter here. And in fact, I could use my mouse and do some little zooming in and out and stuff. If we zoom out, you can see that there's a moon here, there's a moon here, there's a moon here, there's a moon there. Those are the 4 Galilean moons. The Galilean moons are much smaller than Jupiter, so you don't see them very much until you zoom way in. And when they pass in front of Jupiter, the sun is more or less behind us because Jupiter is further away from the sun than we are. And so those moons, when they pass in front of Jupiter, are kind of blocking some of the sunlight. And so I also put the shadows of the moons on the planet Jupiter. And those are called shadow transits. And amateur astronomers love to take pictures of these shadow transits. This is one of the first things that got me interested in astrophotography decades ago, was the hope of being able to take pictures of moons and their shadows transiting in front of Jupiter. Because a friend showed me this through his telescope back 20 years ago. And so this is one of the original things that got me interested in astronomy. And so I thought it'd be really fun to make a 3D version here. Now, of course, you can't do it 3D looking at what I'm showing you here because you don't have the glasses, but the left image goes with the left eye and the right image goes with the right eye. And if you had the glasses and could do that, you would, when the moon comes, you would see the moon in front of Jupiter going across, and the shadow is just on the surface of Jupiter going across, and you get this very nice 3D perspective.
Bob, where is the best place for people to go to take a look at some of your spectacular astrophotography images?
Okay, I'll put that up. That is right here. vanderbei.princeton.edu/images/NJP. And by the way, I think if you just type Vanderbei Astro into Google search, this is the webpage that pops up at the top. So all you really have to know is how to spell my name, Vanderbei.
Wonderful insight. Bob Vanderbei, thanks for taking the time with us and for sharing the interview.
That was great. Thanks for inviting me. This was a lot of fun.